we're going to welcome Fuan and Raquel Moraes to present today on the research project, NRRA research project, the novel methods for adding rejuvenators and asphalt mixtures with high recycled binder ratios. So, if you would like to start out, Fan and Raquel.
Yeah.
Okay.
So sounds good. Thanks, Kurt.
Very good.
Share screen.
Yeah.
Okay. All right. Let's see. Can you see the screen? Okay.
Yes.
All right. Sounds good. Good morning, everyone. It's a great honor to be here. To present this research study that we recently completed for NRRA. My name is Fan. I'm with NCAT, and also Raquel Moraes, who's gonna be with us in a little bit because right now she's teaching a class on campus, and so she'll be here in probably half an hour or so. But I'll be sure to pass along the tough question to her when she joins the webinar. As Kurt introduced, this is a project related to adding rejuvenators in asphalt mixtures with high recycle binder ratios. Before I get started, I do want to acknowledge the research team. Me and Raquel, we got the opportunity and the honor to be here to present this research study. But we do have, Moraes Langen and Dr. Chen Chen, who are a major part of this research team. And they are the one that get the project done and, was able to provide significant research findings. So I do want to acknowledge their contribution. Moraes Langen, she was a former graduate student here at NCAT. She graduated this summer based on this research, and now she's working at the Wallback Group in Wisconsin. And Dr. Chen Chen, he's a research engineer here working with us at NCAT. To start off, I would like to to walk you through how this project, the idea was developed, and then get into some of the test results and the findings and recommendations from these projects that we learned over these projects. As many of us know, over the last several years, or maybe a little bit longer than that, there has been an increasing interest in using rejuvenators to improve the cracking resistance and the durability of high wrap mixes. Recycled asphalt pavement provides significant economic and environmental benefits. But at the same time, because the asphalt binder in the wrap or shingles are much more stiffer, more brittle as compared to the virgin binder. So, in some cases, if we do not design the mix well, those mixtures could have durability or rutting or cracking issues. So one of the ways to look into address that issue is to add rejuvenators. If we look at what has been done in the past about adding rejuvenators, I think there's a significant amount of knowledge on that topic. Specifically on the factors affecting rejuvenating effectiveness, the majority of the study that has been done has been focused on to look into the quality of the products. In that regard, I mean to look into the viscosity reducing capacity and the chemical composition of those materials. You may have heard researchers or practitioners talking about rejuvenator is just an umbrella term, because there are so many products out there on the market, and some may perform better than the others, mainly because of their chemical composition and how they interact with those recycled materials. Another factor that has been recognized in previous research that also affects the rejuvenating effectiveness of adding rejuvenators is the degree of dispersion and the diffusion. What I mean that is how well the rejuvenator is dispersed within the asphalt mixture, and therefore can provide the diffusion and rejuvenating benefits that we are hoping to get out of this chemical additive. But this is a perspective that has not been heavily investigated in previous research. So if we look at the current practice of how to add rejuvenators, I would say the most common approach of adding rejuvenator is called the pre-blending method, which means we are pre-blending the rejuvenator into the virgin binder. Okay, this is something in the lab environment. This is where you can use a low shear mixer, or even using a manual blending to blend those chemical additive into the virgin binder, and then you add those rejuvenator modify the virgin binder and mix that with virgin aggregate or recycled material for preparing specimens for performance testing. In the plant during production, lots of contractors have good experience using like inline blending. This is where like the rejuvenators is kept separated from the virgin binder until during production, where like they are injected into the binder line to mix the two components together, and then this goes into the drum to mix with the other components materials. Besides this, like the most common approach, which is the pre-blending method, there has been some research out there showing like maybe a different way to add rejuvenator is to pre-treat the wrap. In this methodology, the rejuvenator is not added into the virgin binder. Instead, it was added directly into the recycled material. This approach makes sense because like when we talk about the rejuvenator, those are the products that are designed to rejuvenate the heavily aged binder in those recycled material. We are not too concerned about the quality or the rheological property of the virgin binder. It is a binder in the recycled material that are heavily aged, do not have good relaxation property. That's the material that we try to rejuvenate. So adding rejuvenators in the wrap directly provide a direct contact between the recycled material and the rejuvenator, and therefore it has a potential to maximize or optimize, the interaction between the two components, and therefore it could provide, a good rejuvenating effectiveness that we are hoping to get on the mixture performance side. If we look at these two methods, as I just mentioned before, one is adding into the virgin binder, and for that method, pretty much we are adding the rejuvenator to improve the quality of the binder, right? You can consider the virgin binder as a modified binder with rejuvenator. For the other method, where we are adding the rejuvenator into the wrap or the shingles, we are trying to improve the quality of the recycled materials. Well, if you think about our asphalt mixture, which is a composite material including both virgin binders, virgin aggregate, and the wrap or shingles, the quality of the mixture depends on the quality of the virgin binder and the quality of the wrap. So now the question becomes, which of the two approaches is going to be more effective? Is this going to be the one with binder quality, or is that going to be the one related to improving the wrap quality? So those are the questions that we try to answer in this study. And also, when we were the research team here at NCAT, when we were brainstorming this idea, we were thinking like, or is there someone trying to ask a question at this point, or it was just kind of like a background noise? Okay, well, I just assume it's a background noise, and if you have any questions, feel free to put in the chat box or wait until the end to ask the question. We should have enough time for Q&A. So coming back to the presentation, when we were discussing about the research motivation for this topic, we were thinking like, hey, beyond what has been done in the past, which is the pre-blending method or the pre-treatment method, is there anything we can do to those two methodologies that can further enhance the rejuvenating effectiveness of adding rejuvenators in asphalt mixtures with high wrap or rest contents? So there are two ideas that we came up with for research evaluation. The first one is using foaming technology. Our industry is very familiar with the foaming technology because of the Warmix applications. When we do the foaming with asphalt, it creates a significant volume expansion on the binder side, which provide like a better, higher surface area to provide the better dispersion and better mixing with the recycled materials. And also the previous research that has been done related to asphalt foaming show that after foaming, the asphalt binder has reduced binder viscosity, and therefore it can provide a better mixed workability and compactability, which is something we like to have, no matter it is for the lab testing or the field for the field practice. So this is one of the approaches that we are thinking that for the pre-blending method, where we are adding rejuvenator into the virgin binder, can we foam the rejuvenated virgin binder so that we can leverage, the benefits that the foaming technology provide in this regard? So this is one of the motivations that, we came up with saying like maybe we give a shot to see what happens there. And the other approach that we came up with based on the discussion here is is related to the pre-treating method. This is where we're adding rejuvenator into the wrap. But the one concern we had with that methodology is that when we are adding rejuvenator into the wrap or RAS, the amount of rejuvenator is very small as compared to the amount of the wrap or the recycled asphalt shingle that we try to treat. For example, just imagine like we have a 5-gallon bucket of wrap, and then you try to add like maybe 2 gram or 3 gram of rejuvenator into this material. Because of the significant difference in the volume between the two materials, it's going to be very challenging, if not impossible, to achieve a uniform dispersion of those rejuvenator within the wrap, right? We have like maybe like 5 drops of the rejuvenator as compared to 5 gallons of a wrap. It's just going to be challenging. So one thing that we were thinking at that time was like, how can we increase the volume of the surface area of the rejuvenator? Well, there are 2 ways that we can do that. One is pretty much the same approach that I mentioned earlier, which is using foaming technology. In that case, we are not talking about foaming the asphalt binder. We're talking about foaming the rejuvenator, okay? And for the same concept, because of the foaming, the volume expansion, it does provide a bigger, significant larger volume and the surface area to provide the coating. And therefore, it could provide a better dispersion within the wrap. The other approach to increase the volume of the rejuvenator is to use emulsion technology. This is where we introduce a significant amount of volume of water in the products so that it give us a better chance to achieve better dispersion of the rejuvenator in those recycled materials. So the 2 pictures that I showed here are just kind of like illustrations of how the technology works. The one on the right, on the left side is foaming. As you can see, like there's lots of foaming bubbles created, and that's where like it provides the volume expansion. And also on the right side, this kind of like a simple illustration for the emulsion technology. This is where we're able to add to the water, and also with emulsified agents there, we're able to significantly increase the volume of the products. So those are the approaches that we came up with, saying like, hey, this might be something that can further improve the current practice, which is either we add rejuvenator into the virgin binder or adding the rejuvenator directly into the recycled material. So with that being said, the overall objective of this research is to explore those 3 alternative methods of adding rejuvenators. And more importantly, what we are most interested in is to determine their impact on the workability and the cracking resistance of high wrap mixes. At the end of the day, it is the performance properties of those mixtures that we are most interested in, because those are the properties that may give us better correlation to how those materials are going to behave in the field. Okay, so the 3, just to kind of like to refresh, what we discussed so far, the 3 methodologies are listed here. The first one is what we call like a foaming enhanced pre-blending method. For this method, we are pre-blending the rejuvenator into the virgin binder, and then we're going to foam the rejuvenated virgin binder for mixing with virgin aggregates and the recycled material. The second approach is what we call the foaming enhanced wrap pretreatment method. So in this case, we are adding rejuvenator directly into the wrap instead of the virgin binder. But in order to create a higher volume of the rejuvenator, we are using foaming technology to foam the rejuvenator before adding the rejuvenator into the wrap for pretreatment. Okay. The last method that we evaluated in this study is what we call emulsion-enhanced wrap pretreatment method. This approach is very similar to the second approach, with the only difference between the 2 is, approach number 2 use foaming technology. Approach number 3 use emulsification technology to increase the volume of the rejuvenator. But in both cases, the rejuvenator is added into the wrap as a pretreatment, instead of adding into the virgin binder for pre-blending method. Okay, so those are the three alternative methods that we evaluated in this study. In terms of experimental plan, we set up the experimental plan based on like 4 tasks. From the very beginning, what we did was to characterize the rejuvenator to better understand, the wettability and the viscosity of the rejuvenator, because those are the 2 properties that can affect the foaming behavior of those rejuvenator. Okay. And after that, we did a foaming experiment, try to optimize the foaming conditions when we try to foam rejuvenator or the virgin binder that has been modified with rejuvenator. And then after that, we tried to look into the wrap pretreatment and the marination. This is where we're looking to like how adding rejuvenators affect the quality properties of the wrap. Okay, and also we try to look into marination. Marination means like after you adding rejuvenator into the wrap, you keep the material for an extended period of time, hoping that we would get better dispersion or better interaction between the rejuvenator and the wrap. Okay, this is what we mean by saying marination. And the last part of the study was focused on mixture performance testing. As I mentioned before, this is going to be a major key part of this research, because at the end of the day, we want to look at those performance tests to tell us like, does those methodologies work or not work? Okay, so that's kind of like the 4 approaches for experiment that we did as part of this research. And for the next few slides, I'm going to walk you through like one experiment one by one and provide some of the research findings that we learned or we obtained from those experiments. So the first part, as I mentioned earlier on the previous slide, is to characterize the wettability and the viscosity of the rejuvenator. In this study, we selected 2 bio-based rejuvenators, and we look at like for each of the product, we look at both 2 different forms. One is what we call like the original form. So this is the products that you get, straight from the supplier. This is kind of like what they call like, as provided rejuvenator. And also by working with the rejuvenator supplier, we were able to obtain the emulsion form of those rejuvenator. The picture that I'm showing in here, the 2 on the left side are the as provided original form of the rejuvenator, and then the 2 on the right side are the same products, but it has been modified with emulsify agent and with water. So this is what we consider the emulsified rejuvenator. Because this study is not about comparing A product versus B product. It's more about using the same products but look at the different ways of adding rejuvenator. So we decided to just keep the not disclosing the product name, but instead of just calling it RA1, representing the first rejuvenator evaluating the study, and RA2 for the other products. In terms of characterization, what we did was to look into the wettability and the viscosity. For the wettability, the test we used was called like a Cecil drop test, which is a methodology that allows us to measure the contact angle with asphalt binder. So it gave us a little bit of indication about the wetting potential between the rejuvenator and the asphalt binder that we're going to use for the high wrap applications. On the viscosity side, it's a pretty standard test. We are using the Brookfield with rotational viscometer to measure the viscosity of the products at various aging conditions. One thing I would like to mention here is for both tests, we are only testing the rejuvenator, not the asphalt binder. Okay, this is more about characterizing the products, the properties of the rejuvenator products. And then these results help us understand how these materials behave when we try to foam them. And this is something that's, we try to collect those information up front. If the test result shows like maybe there's some potential issues for foaming, we may need to do some modification to the products to increase the foaming behavior of the material. But the two products we selected here have pretty good wettability and viscosity, and they showed pretty good foaming behavior. So that's why like we did not do any further modification. But some of the work that has been done in the past that have shown that you can add like a surfactant into those rejuvenator, try to change or modify those properties of the product so that it will be easier to foam on those rejuvenator. The second part of the study was focused on the foaming. The objective of that experiment was try to select the optimum foaming conditions of the rejuvenators and the rejuvenated asphalt binders. So when I say rejuvenated asphalt binder, those are the virgin binders that has been pre-blended with rejuvenator. And then, we put those material in the foamer and try to foam that. In this experiment, what we used was a vertical foamer, as you can see on the picture here. And then in order to quantify the foaming behavior of either the rejuvenator or the rejuvenated asphalt binder, we use a laser distance meter attached to the foamer so that we can collect how much volume expansion or how much volume collapse this material went through during the foaming process. So the way the test setup is very straightforward. So, this is a vertical foamer, and over here, this is the foaming nozzle. This is where the rejuvenated asphalt binder or the rejuvenator can shoot out from the device. And then what I try to highlight with my pointer here is a laser distance meter. So pretty much it shoots like a laser, points, to the bottom of the can. Okay, so it gives us like a height measurement or distance measurement between the bottom of the can to the position of the device. So during the foaming process, as we get more, liquid in the can, the height is going to change, and this is where we'll be able to apply some data analysis to the data and to calculate the foaming behavior of those materials. So this just gives you an idea of the laser distance meter data that we collected from one of the foaming trial. So, this is on the y-axis, it's a distance measurement, and on the horizontal axis is time. So before we started foaming, so the laser was pretty much pointing at the very bottom of the can without any rejuvenator or asphalt binder, so the height didn't change. And then once we started foaming, that means like the liquid gonna shoot out from the foaming device into the can or into the 5-gallon bucket. And this is where like the distance gonna change. And then there'll be a peak number, at a bottom number, a lowest number in terms of the distance, because this is where like we got the highest, volume expansion at that time. And then after that, the foaming gonna collapse because like, based on the thermodynamics, the foaming is not gonna be stable. That's why like the height is gonna drop. And therefore like the distance between the top of the liquid that we measured gonna increase. And at the end, like, once all the foaming bubbles are gone, like we're gonna reach a constant or pretty stable height. So this is kind of like the raw data we got. And then, with some of the measurement we have, we'll be able to apply data analysis to the distant data to convert the height into volume expansion. So, this is the plot I'm showing here on the right side. This is, the volume expansion curve after we apply the data analysis. So pretty much like the first data point indicates is the maximum instantaneous volume expansion that we got out from either foaming the rejuvenator or foaming the rejuvenated asphalt binder. And as I mentioned before, foaming is not going to be stable. Therefore, the foaming bubble is going to collapse. And because of that, the volume expansion going to drop. And this is what we saw with the data. And then like with all the data calculated here, we can apply a curve, to kind of like to predict, if you will, the foaming, the volume expansion and the collapse behavior of this material. For those of you who are familiar with foaming, I think the two parameters that have been widely used in previous research is to look at the volume expansion. So the first point, the maximum volume expansion, and also half-life. So half-life is defined as the time required for the foam to drop to half, 50% of the maximum volume, okay? So the maximum expansion ratio tells us how much volume expansion we got from those material, and half-life give us a little bit of indication about how stable that foam material is. You know, if the foaming is more stable, that means like it's going to take a longer time for it to collapse to 50% of the peak volume. But some of the work that has been done as part of NCAT 953 at Texas A&M University show that those are the point measurement that may not be sufficient to characterize the entire foaming behavior. And because of that limitation, the research team working on that NCAT project recommended looking at the entire curve and look at the area under the curve as an indicator to describe the foaming behavior. When we look at the area under the curve, it will cover both, you know, how much the volume expansion you get at the beginning, and also the relative stability of the foam material. So that's kind of like the parameter that we used in this study, which is what we call FI, standing for foamability index. In this case, a higher number is what we like to get for foaming, because that means you get a decent volume expansion and also you got a good stability over time. So now providing a little bit of detailed information about the different material that we did in the foaming experiment. As I mentioned before, we included the two rejuvenators referred to as RA1 and RA2. And then in terms of foaming conditions, based on the previous research on asphalt foaming, we know the two factors that have a significant impact on the foaming behavior of liquid are temperature and water content. So that's why we select the three temperatures here, the lowest temperature being 110 degrees C, and the higher temperature being 130 degrees C. And the other parameter factor that could affect the foaming behavior is water content. So this is where how much water you add to create the foaming of those material. And we are looking at 1%, 2%, and 3%. So with three factors for each variable, we are able to evaluate 9 combinations of the foaming behavior. And based on those measurements, we'll be able to identify what is an optimum combination of foaming temperature and foaming water content that can give us the best foaming behavior. For the rejuvenated asphalt binder, this is where we are pre-blending the rejuvenator into the virgin binder. Once again, we look at the two combinations of materials. RA1 was used together with the PG6422 binder, and RA2 was used with a softer PG58S28 binder. Similar to the Rejuvenator foaming experiment, we look at a combination of 3 foaming temperatures varying from 130 to 150 degrees C, and the 3 water content from 1% to 3%. One thing you probably recognize that the foaming temperature that we used for rejuvenated asphalt binders are higher than the temperature we use for the rejuvenator. We did that intentionally because the rejuvenated asphalt binders have much higher viscosity as compared to the rejuvenator. And therefore, we decided to increase the temperature, the foaming temperature for the rejuvenated asphalt binder, so that it will have a better chance to provide the foaming benefits that we were hoping to get. So this is just an example showing the foamability index result that we got for one set of the rejuvenator that we evaluated. As I mentioned before, 3 test temperatures. Each temperature look at the 3 different water content. So the 3 bars over here is 110 degrees. The 3 bars in the middle, 120 degrees C, and the one on the right side is 130 degrees C. And the length of the bar indicates the foamability index, which is the area under the volume expansion versus time curve that I mentioned earlier. So keep in mind that a higher foamability index is what we want in terms of the foaming behavior. In this case, as you can see, it's very obvious that the last bar, which corresponds to 130 degrees C foaming temperature and the 3% water, give us the best foaming behavior. And therefore, based on that results, for this specific rejuvenator, we selected this combination as optimal foaming condition for further evaluation of the study. And we apply the same, methodology, data analysis methodology to all the test results we collected from this experiment and use that for further evaluation when we try to do the wrap pretreatment and wrap marination experiment. The third part of the study is to look into the wrap pretreatment and marination. The whole idea is to determine the pretreatment and marination of the wrap quality properties. For this experiment, we only look at one rejuvenator and one wrap. The wrap used here is from Alabama. That's where where NCAT is located. And we extracted the wrap binder out from the material and determined the Ph.D grade, and it came out to be a Ph.D 100 class 2. Okay, and we also look at the delta TC is minus 7.3 degrees. So I think as everyone knows, when you look at the Ph.D grade like that with that negative delta TC, that just shows like how heavily aged that material has been in terms of wrap. For the pretreatment part of the experiment, we look at the three methodologies. One is what we call spray on. It goes back to the earlier discussion that I had. How can we achieve uniform dispersion of the rejuvenator? If we just drop the rejuvenator into the wrap, it's not going to work, most likely because of significant volume difference between the rejuvenator and the recycled material. So one approach we did was to use a spray bottle. That is not really ideal, but it does provide a little bit better dispersion, at least to the surface of the wrap, and that's what we call like a spray-on methodology. The second method was using the emulsion technology. This is where we got the emulsified version of the rejuvenator, and which have a significant higher volume as compared to the original form of the rejuvenator, and therefore it has the potential to provide a better dispersion. And then the last method we used was foaming. So this is where we put the rejuvenator into the foaming device, and then we foam the rejuvenator at the optimal foaming condition that is selected in the previous experiment. And the foam rejuvenator going to be dispersed into the wrap, and then hopefully because of the volume expansion and the increased surface area, it can provide a better dispersion. And for each of these methodology, we try to maintain the same mixing procedure. What we did over here is to mix in the wrap with the rejuvenator for 2 minutes in the vertical impact mill. In this case, the wrap are not preheated, so those are room temperature wrap. So what we try to simulate is that during production or ahead of production, you have the wrap stockpiles. You try to pre-treat the wrap stockpile with rejuvenator without applying the heat, and to see if whether or not that's going to provide a good rejuvenating effectiveness on the mixture performance side. The second part of the experiment focused on marination. This is where after adding rejuvenator, we keep the rejuvenated wrap for a longer period of time, hoping that it provide additional time for the rejuvenator to diffuse into those recycled materials and to provide a better, physical and chemical interactions with those recycled materials. We look at two sets of marination conditions. The first set is what we call accelerated marination condition. We call it accelerated because it was done at a higher temperature, so at 135 degrees C. And in that case, we were using a 1.5 hour or 3 hours. So those time and the temperatures were selected based on some of the recommendations from asphalt contractor in Japan who have experience or successful experience using marination for high wrap mixture production over there. The other set of marination condition is what we call extended marination. In this case, we are using a much lower temperature. Instead of doing 135 C, we are doing ambient temperature, which is not applying any heat. But because of a lower temperature, we decided to look into a longer time, so that it gives provide a better chance for the rejuvenator to diffuse and interact with those recycled materials. And the two durations we look at is 3 days and 7 days. But once again, those are at ambient temperature without applying heat. In terms of wrap quality characterization, we look at the different tests on the wrap itself, including the downgrade workability test to look into the workability of the material. We also, after we compact the DWT samples, we ran Cantabro tests on those samples to indicate or to evaluate the overall durability of those materials. And also we look into what we call like the grayscale based image analysis. I'll provide a little bit more information on that, but pretty much by doing the image analysis, it gives us indications or information about the appearance and also the color consistency of those wrap after you add a rejuvenator to it. In addition to just testing the wrap, we also look into the extracted binder. For the marination samples, we look at the DSR and the BBR testing to look into the rheological properties. And also we did some serifraction testing on those extracted binder to look into the chemical fractions of the extracted binder from the wrap after pre-treated with rejuvenator. So for the image analysis, it's a very straightforward approach for what we did. So as you can see at the bottom of the slide here, we got office scanner that many of us have used in your office. And then we put the wrap material on top of the office scan and then office scanner and then scan the picture of the wrap. And then this is the image you got, okay? And it's pretty, regular picture that you would see when you try to take a picture of the wrap. And then in this case, it's a very fine graded wrap, so that's why you're not going to be able to see too many aggregate particles. But depending on the gradation of the wrap, you may get different images. And then we apply a software that we developed here to try to quantify the grayscale distribution of this image. And after you apply that analysis or calculation, this is a plot you got. So this is pretty much a grayscale distribution plot. So a lower number locating on the left side of the grayscale horizontal axis indicate a much darker color, okay, a black or darker color. If you have a higher number of the grayscale, that means you got a very light color, okay? And then that will tell you the overall distribution of the grayscale among the image that you get. In addition to just look at the location of the distribution plot on the grayscale, we are also interested in looking to the weights of the distribution plot. That indicates the color consistency of this material. For example, if you have a perfectly homogeneous material, the weights of this distribution plot are going to be very narrow, which means it's highly consistent. But if you have a wrap material that's, the color is not consistent, that means that you may have uncoated particles, or you may have some wet or dry spot, depending on where the rejuvenator were added. In that case, you're going to have a much wider distribution plot that just indicates, lack of a color consistency. So that's how it works. Now I'm going to show you some of the test results that we got from these experiments. In this case, the plot that I'm showing here is, the DWT, the workability test results that we got on the wrap. So there are 4 sets of bars. The 2 on the left side are what we consider the control wrap. Those are the wrap material without adding rejuvenator, okay? And then the 3 set of bars on the right side of the picture that I try to highlight with my pointer are the pre-treated wrap. Those are the ones that you added rejuvenator on top of the wrap and do a 2 minutes mixing using the pug mill. But the difference between the 3 set of bars are how the rejuvenator were added. Over here, we were using the spray-on method. Over here, we are using the emulsion method. And then the set of bars on the very right side are the one using foaming technology. So as you can see here, when you look at this to compare, when you try to compare against the control wrap, which is untreated wrap, you can see adding rejuvenators improve the workability of the wrap. regardless of which methodology we are using, okay? And also we saw the same thing on the grayscale image analysis. There are 4 sets of curves corresponding to the 4 wrap sample that we tested. The blue curve is a control wrap. This is a wrap without adding rejuvenator. As you can see, it is located on the right side of the grayscale as compared to the other 3. That means it has a higher average grayscale number, which indicates that it has a lighter color as compared to the other 3 samples. And then the orange, the gray, or the yellow color curves are the one that after you add rejuvenator to the wrap. As you can see, once we add rejuvenator, the curve is shifted to the left side of the scale, which means we are getting overall darker color on those material because of adding rejuvenator going to get some of the binder activated. And the other thing you're probably going to notice is that the distribution plots for the control is much wider as compared to the wrap after adding rejuvenator. Once again, as I mentioned before, the weights of the distribution plot indicate the color consistency. So what we are saying is adding rejuvenators using emulsion or the foaming technology provide a better dispersion of the rejuvenator. And because of that, it gives us a more consistent color appearance on the wrap as compared to the one that we got using the spray-on method or the untreated wrap. So based on all the test results that we look at, in addition to just these 2 plots that I'm showing in here, we found out that the emulsion pretreatment method was slightly more effective than the spray-on and the foaming method. And that was the method that we decided to use for the marination experiment. And when we look at the marination experiments, this is the same set of results that I showed on the previous slide. The one on the left is DWT, workability evaluation. The one on the right is a grayscale image analysis. In this case, there are 5 sets of data. The one on the left is no marination. This is what we consider the control set. And then the other 4 are the ones with different marination conditions. As I mentioned before, we have two temperatures, 135°C for 1.5 hours and for 3 hours. And then we do the room temperature or ambient temperature for 3 days and 7 days. But if you look at these results, you probably recognize there's not significant difference in the DWT result among all the samples that we tested, no matter, the marination condition. And we saw the same trend on the image analysis. Pretty much the 5 sets of curves are overlapping each other, which means they have, reasonably similar color appearance and consistency. So based on these results, we are saying that marination did not significantly affect the wrap quality properties. In addition, just to look at the wrap, testing of the wrap, we also look at the extracted binder. This is where we look into the PG grade, look into the MSCR and the frequency sweep, and also look into the Sarah fractions. One interesting finding that we got when we look at the marination based on extracted binder is that when we do the marination at 135°C, actually it has a detrimental impact on the binder properties. Okay, as I mentioned before, the idea of doing marination is to provide longer time or duration for the rejuvenator to diffuse into the recycled material and provide better, rejuvenating effectiveness. But when we age the material at 135°C for marination, asphalt aging also happened. So now we got 2 factors going on at the same time. One is rejuvenating, which is going to provide a better performance, at least from the cracking or the durability perspective. But at the same time, because of high temperature used for marination, the asphalt binder is going to become, more aged. So it's kind of like the battle between the 2. And based on the test results that we got from this marination experiment, we found out that the impact of aging was more significant or more pronounced than the impact of rejuvenation. So this interesting finding just highlight that when we talk about the marination, we want high temperature to accelerate the diffusion and interaction. But at the same time, we need to be cautious about additional aging that the high temperature introduce. So what is a good balance between in terms of temperature that can give us the optimum combination of rejuvenation with the impact of aging is something that needs to be further evaluated. But at least based on what we saw at 135 C, that's probably going to be too high because the aging overshadows the benefits from the rejuvenation. The last part of the experiment was to look into the performance testing. As I mentioned, the objective was to determine the impact of different rejuvenator application methods on high wrap mixture performance properties. In this experiment, we look at the two high wrap designs. One is 9.5 millimeter mix with 45% wrap, and the other one is 12.5 millimeter mix with 50% wrap. So those are definitely high wrap mix designs. For each of the mix design, we fabricated and tested 5 mixtures. Okay, the first set is what we consider the control mix without rejuvenator. Okay, the second one is pre-blending the rejuvenator into the virgin binder. So if you will, you can consider this the common practice of adding rejuvenator. This is probably the most popular way of adding rejuvenator in the lab for all the previous research. And then the next two, this is the alternative method that we evaluate in this study. We are adding the rejuvenator into the wrap for pretreatment, but in order to provide the better dispersion that we are hoping to get, we are using the emulsion technology and the foaming. So one is to emulsify the rejuvenator, one is to foam the rejuvenator. The last mixture that we evaluated is what we call like a foaming enhanced rejuvenated virgin binder. This is where we're still adding the rejuvenator into the virgin binder, but after that, we're gonna foam the rejuvenated virgin binder. And because of the volume and surface area increase and the viscosity reduction benefits, hopefully that can provide a better dispersion or better interaction of the rejuvenator with those recycled materials. The tests we look at include the DWT for workability evaluation, ideal CT for intermediate temperature cracking resistant evaluation, and the DCT for the low temperature cracking evaluation. We recognize the importance of asphalt aging, so we decided to do long-term age samples for the cracking evaluation. The aging procedure we use here, it's 4 hours at 135 C for short-term aging, and after, excuse me. And after that, we did additional 6 hours loose mix aging for 135 C. Okay. For Moraes' thesis, she volunteered to do some additional tests to provide additional information for the research. And we included the Cantabro test and the IFE test for the evaluation of different ways of adding rejuvenators. We got lots of test results from this experiment, but because of the time limitation, we're not going to present all the data. What I'm going to do is to provide an example using ideal CT and then provide the conclusion that we got based on all the test results we obtained from this experiment. So this is a example set of ideal CT results for one of the 45% wrap mixes. As I mentioned before, for that mix design, we included 5 mixtures. So the one on the left is a control mixture without rejuvenator. The second one is what we call the pre-blending approach. So we're adding rejuvenator into the virgin binder. These two are the ones that we are adding rejuvenator into the wrap, but using emulsion and foaming technology. And then the one on the very right side are the one that we are foaming the rejuvenated virgin binder. Okay, so this is how the data, how the mixtures are listed here. So when we look at the data, the first comparison we did was, the rejuvenated mixes, no matter how rejuvenator was added as compared to the control. In this case, for ideal CT, a higher number is better in terms of the intermediate temperature cracking resistance. As you can see here, the 4 mixtures with rejuvenator have a higher CT index as compared to the control, which indicates that in general, adding rejuvenators improves the cracking resistance of the mixture. And we saw the same trend on the workability and the DCT data. The next set of comparison is to look into the different ways of adding rejuvenator. This is where we compare the 4 bars on the right side of the plot. As I mentioned before, mix number 2 over here and mix number 5 are using the pre-blending method. But 5 includes the foaming technology, 2 was just straight blending of the rejuvenator. And then mix number 3 and mix number 4 are the pre-treatment method. If you compare those 4 mixtures, as we can see from here, the pre-blending mixtures have higher CT index number, indicating like a better intermediate temperature cracking resistance than the other 2 mixtures that we added rejuvenator using the pre-blending method. And we saw the same trend on the workability and the DCT data. So based on that, we're saying like the pre-blending approach provide a better rejuvenating effectiveness as compared to the RAP pretreatment method. And finally, when we compare to the 2 pre-blending method, this is a straight blending, and then the one on the right side is a foaming enhanced pre-blending method. In this case, we recognize that foaming rejuvenated virgin binders slightly improve the workability of the mix, but they did not have significant impact on the cracking resistance of those mixtures after long-term aging, which apply to both the ideal CT, and the DCT test that we included in the experiment of the study. So based on all the test results and findings of the study, our recommendation is that it's for asphalt contractor to continue to use the pre-blending method to add rejuvenator for high RAP mixes for 2 reasons. One is on the performance side, based on the lab testing that we did, it provides a better performance test result as compared to the approach of adding rejuvenator into the RAP, okay? And the other reason is more about the practicality side. Definitely from the plant operation perspective, pre-blending the rejuvenator into the virgin binder going to be so much easier to handle for production operation side. As I mentioned before, lots of contractors have successful experience using the inline blending. This is something that has been used for adding other asphalt additive like warm mix asphalt or liquid anti-strip additives. For the asphalt contractor who already have a foaming device installed on their plant, we recommend them to consider using the foaming enhanced pre-blending method for several reasons. One is based on our test result that, because of the foaming technology, it does improve the mixture workability for those mixtures, including high RAP. And because of the better workability, it has the potential to give us better compactability in the field. And that's always something that we like to achieve. And also with the foaming technology, it provides a potential to allow the contractor to reduce the mixture production temperature. And because of the reduced temperature, it could provide significant economic and environmental benefits as warm mix asphalt. As our industry moves towards, the net zero goal, try to reduce the carbon emissions, this is a potential approach that can help us to achieve that goal at the same time, provide equal or if not better performance on the mixture side. The study that we did here showed a very promising result of using the DWT to look into the quality or the workability of the RAP. This is something that we have been continued to look into, at least here at NCAT and in some other ongoing projects that we collaborate with other researchers to evaluate DCT as a potential tool to assess the quality and the consistency of the RAP stockpiles. The current practice is to look at the binder content gradation or determine the PG grade. But that process can be very time consuming, right? Especially if you try to determine the grade of the binder, involve the solvent extraction, recovery, and testing. So the DWT testing does not require those procedures. All we are doing is testing the RAP material as sampled. And if the results make sense, it will give us some indication about the quality or the consistency. This is something that we have been looking into for some ongoing research here at NCAT. With that, that's kind of like the research result and findings. I do want to acknowledge, the Minnesota Department of Transportation for funding the study and Blackledge for providing cost share to the study as our industry partner. Throughout the project, we work closely with the TAP from NRRA, and those are great people that provided feedback and guidance on the research approach and the implementation. So appreciate their support and guidance throughout the project. And also want to acknowledge the material suppliers that are working with us to provide the raw material, including rejuvenators, mix designs, the raw aggregate binders for us to do research evaluation. So thank you for your assistance. With that, thank you very much for your time and attention, and I will hand it back to Kurt to see if there's any questions in the chat box or from the online participants about what I presented so far.
Okay, thank you, Fawn. It was an excellent presentation.
Thanks, Kurt.
Are there any questions? I see there's a couple of chat questions, but maybe if you'd just like to, we've got some time for a little bit here for some questions directly. If you just raise your hand. And Ken, I see you had a couple there. Maybe you would like to just join in.
Yeah, Kurt, and it's a long comment because my mind always works a lot faster than my keyboarding skills. But I think the first one was kind of looking at a plant application, and there's a lot of similarities when you look at the comparison between like using hydrated lime or look at anistrips back some ways back. And so I was wondering if there was some way to incorporate the addition of the recycling agent during the milling process. And even though we typically don't use all the mill tailings in basically production mix, it sets the remaining part of that stockpile up as a usable product for binder courses or other uses. But so that's kind of what that addresses, that first long comment. The second comment, I guess, Fawn, and great presentation, love the approach, is on number 4, phase 4, was the ideal CT the only performance test to characterize fatigue cracking? And did the DCT testing show any additional differences? And of course, in our part of the world, it's always the cold temperature cracking that comes into play very quickly too, with brittle wrap mixes. So I'd just like to hear your comments or assessment of that. So I'll get off here.
All right, appreciate the comment and questions, Ken. Regarding the first part of the comments, I think that's a great idea. I think, earlier this year in one of the discussion here at NCAT, someone brought up the idea of maybe we introduce the rejuvenator during the milling operation. That way, like as sampled wrap, from the project has already been processed or rejuvenated. Personally, I think that is a potential approach. I'm not aware of any research looking to that, specific, process and how that's going to affect, the performance of the mixture or, the plant operation side. But I do think this is at least a good approach to look into maybe for future research. The second part of the comments or question was related to the performance testing. We did ideal CT as kind of like the intermediate temperature cracking resistant because, if you look at where we are in terms of balanced mix design implementation among state highway agencies, I think that is the most popular test. So that's what we used. And then on the low temperature side, we look at the DCT. In general, those tests, at least in this study, they provide very similar conclusions in terms of the comparison between different rejuvenator application methods. There are cases where they, provide a little bit different directions, but in the ballpark, they agree with each other, including the workability test that we did on the mixture. And also, as I mentioned, we also look into the Cantabile and iFit because of, the additional work that Moraes volunteered for her master thesis. And they all show the same, very similar trend. So at least like in this study, those performance tests on the cracking side, they tend to agree with each other relatively well. But I'm not saying those tests are the same, but in terms of the comparison between different rejuvenator application methods, they provide similar conclusions.
It looks like we have Thank you, Ken. And it looks like we have another chat. Do you think pre-blending from Irvin? Do you think pre-blending the Rejuvenator into the binder would improve foamed CRR project performance?
Yeah, I think it does. At least based on what we show on the, I know it's on the high wrap recycling application side, it does provide the benefits. So I guess the question I'll be interested in knowing is when the two different methods, are you adding Rejuvenator directly to the wrap, or you try to add into the binder? Even for for the foam CRR, you could add the Rejuvenator into the binder and foam it. So there are two approaches that can be incorporated. I think maybe some research needs to be done to understand or to compare the two approaches and saying which one is more effective than the other. Maybe they're equivalent, maybe one is better, but I think either way it should provide some benefits as compared to not adding Rejuvenator for that application.
Okay, thank you, Irvin. I wanted to I skipped over John's. It's somewhat of a any thoughts on RA treatment during full depth recycling with foamed asphalt?
Yeah, I think this is kind of like the same, very similar comment to what Irv just asked. So hopefully what I provided was it answered that question too.
Okay, and anyone else questions for Fawn? Okay, well, that sounds great, Fawn, and thank you, Fawn and Raquel, for delivering this great research, and the rest of the team at NCAT for delivering this great research to us.
Well, thanks, Kurt, and thanks for the opportunity. And I have shared our contact information for any of you who are interested in getting more information about what we learned. Feel free to reach out, and we'll be glad to talk to you about more about these projects.
Mm-hmm. Okay, very good. Thank you, everyone, for joining in today, and we'll see you next month.
Okay, thanks, everyone. Bye.